Welcome to this topic video on the JavaScript concurrency model. This is our start. This will be our start of asynchronous JavaScript. So our learning objectives here are to get a basic view of JavaScript's runtime model, to review some methods for dealing with concurrency, okay, and use the event queue with callbacks to understand issues with this approach, okay? So this is the basis for JavaScript's runtime asynchronous processing model, okay? Readings and references. First of all, there's some example code that you can go download, okay? I'll be showing you examples from that, okay? Some of that code is available right in this slide set. Most of this is based on the concurrency model, the MDM reading, so read that carefully. Okay. And we're going to be using the set timeout function. We're going to learn about that for controlling the event queue. Okay. In addition, a more sophisticated model, but based on the same model, is Node.js's event loop. Okay. So that's good information, not required reading for this course, but they get a little bit more sophisticated because they're a little bit more performance oriented. So, in a picture, the JavaScript runtime model consists of, well, this isn't unusual, Professor, the stack, the heap, okay, those two things let's discuss, that'll be a reminder, okay, but what's different here is not the stack or the heap, but the queue, okay, so let's recall. What's the stack? That's memory used for function calls. Okay, stack frames consist of function arguments and local variables. Every time a function gets called, you got to save some stuff so you can come back out of that function. That's what the stack is for. Okay, hence the famous issue of stack overflows when you have recursion or other issues going crazy. In JavaScript, okay, the heap is where all variables, memory is for all variables and objects is kept. Okay, so that's the main place where all our variables are kept and things. Okay, stack for function calls, heap for all other memory needs, and then we've got this thing called the message or event queue. This is how we're going to deal with concurrency. It's a simpler notion of concurrency than you might have seen in an operating system class if you've taken one. Okay. So what are some common concurrency mechanisms? Okay. One thing you may have heard of is a process. Okay. A process is implemented by the operating system. Processes get separate protected memory spaces, okay? And more than that, they're their own program, they're their own entities. They can contain multiple threads, but they get protected memory spaces, okay? So not only do they have processes, but they contain at least one thread. Where would we use these? Well, it turns out, nowadays, most browsers, Firefox and Chrome, use a separate process for each tab, okay? That protects one tab from another, okay? Because they have protected memory spaces. Something goes wrong, and really wrong in one tab, it's not going to affect the other, okay? Usually not, okay? Because these are protected memory spaces. This is also the highest in overhead, okay? Second, and which you may have seen or may not have seen, is something called threads. Once again, usually implemented by a runtime or the operating system or a library, but this is pretty detailed things, okay? Why do I say that? Because threads each get a separate program counter. What's that, Professor? That's the thing that keeps track of where you are in your program, okay? So threads generally have hardware support, okay? So it gets all the way down to the hardware. Processes definitely have hardware support because that's what memory management units are for, and they help protect those memory spaces. Threads also have hardware support. Okay, so this is close to the metal, very general mechanisms for dealing with concurrency. Okay. However, it's not easy to program with in general. Okay, if you're getting down and dirty into operating system stuff, okay, drivers and stuff like that, you are going to need to understand some of that. Okay, there's all sorts of issues with deadlocks and such like that. Okay, for your information, here's a decent reference for threads and processes. Okay, none of this is strictly required for this class, but to understand. Okay, JavaScript does something different. JavaScript, the runtime, uses a message queue. Okay, so JavaScript, when we run JavaScript in the browser, in our tab, there's some kind of runtime to run it. How does it deal with asynchronous operations? It uses something called a message queue, which is a list of messages to be processed. Each message has an associated function which gets called to handle the message. Okay, makes sense. So intuitively, this is pseudocode, we'd have basically something like, while we're waiting for a message to get dropped in the queue, as soon as something gets dropped in the queue, we process the next message. Okay, and we go over forever waiting for that. Now, and the reality is, if you wanted to do a loop like this, you would need some thread-like functionality to get it to work. Okay, what we need to understand is the event loop from the point of view of the consumer. Okay, what's going on underneath by the JavaScript runtime is something like this. Okay, we are not going to interface at that level. We're going to interface with the event loop. Okay, so process. Okay, what is a queue? Okay, a queue, especially if you're not from places that use that language frequency, is a waiting line. Okay, it's an ordered structure. Things go in one place, come out the other. Okay, processing an event or message involves calling callback functions. We've been dealing with those. Processing an event message involves calling the callback function with parameters corresponding to the event or message. Now, this callback function that gets called is run to completion. Okay, run to completion. This is also known as non-preemptive scheduling. Okay, this is different than what's happening with your operating system dealing with processes. Okay, where it's going to share the processor amongst different processes. When a callback gets called, okay, in the event loop model in JavaScript, that callback function is run until it's done. Okay, this is a simplified asynchronous processing model used by the JavaScript runtime. Okay, in web browsers, messages are added anytime an event occurs, and there is an event listener attached to it. If there's no listener, the event is lost. Okay, so if I click on this screen, I'm trying to click on the screen, okay, a click event could be generated by this part of the DOM. Okay, if there's nobody listening, no event listener is attached for it, the event is lost, is gone. Okay. Oh, so this is how this is how the events get processed. Okay, so we've seen tons of DOM events, right? All sorts of GUI events, right? On mouse in, mouse out. Oh no, mouse enter, mouse out, mouse down, double click, click, change, etc. We've seen all sorts of GUI events. Okay, so this is how we get our GUI events. Okay, and so that, what do I mean run by completion? When the GUI event fires, the event listener gets called. Okay, nothing else is going to run until that event listener, the little functions that we write, complete. That's why we try not to do anything too long and tedious. We don't go and do machine learning things in event listeners or things like that. Okay. Other types of events, network on and offline events, WebSocket events, and more. Okay. Implicit events, my terminology, when a timer or an interval expires, fetch call returns, that's kind of a network event, okay, and more. So this is, we've been using this already, okay. Now, we can make our own events. We can add something to the JavaScript runtime event queue, okay, and it's going to look like we're doing something to do a timer, use a timer, okay? But the thing is, okay, we're going to use this set timeout function, okay? Scope, this is always going to be window scope for us, could be global scope in Node.js, okay? We're going to use the set timeout function. We give it the callback that we want that event to be called when the event happens. We have an optional delay. Okay, we can give it a delay in milliseconds. Okay, optional, the delay is 0 and is optional, it defaults to 0. Okay, so let's look at an example. Okay, I modified this from MDN just to be a little clearer. Okay, so what am I going to do here? Console log, this is the start. Set timeout function CB1. Why did they say CB1? For callback 1. This is a message from callback 1. Console log. This is just a message. Okay. Set timeout function callback 2. Console log. This is a message from callback. Why are you bothering with all this, Professor? Well, the reason is we want to understand how the event. Yeah, this seems very trivial. We want to understand how the event loop works. Yeah, Professor. Okay, so the question I have is, what's this thing going to do? What's this code going to do? All the timeouts are set to 0. What's this going to print out and why? Okay, so you're going to take that code, you're going to hit the little copy button, you're going to come into your browser, and you're going to go, okay, yeah, right, obvious, Professor. What? This is the start. This is just a message. This is the end. Why did it skip these guys? So this printed out. Let's look at it. Come on. Wait a second. This is the start. Makes sense. That's at the beginning. But somehow it skipped this callback thing and said this is just a message here. See? That corresponds to this here. Okay. This is the end. We're already finished. We're finished and the other guys didn't do anything. Okay. This is the end. Then we get a message from callback 1. This gets called. Then we get a message from callback 2. This one gets called. Why? Oh, the event loop. There's 2 rules to figuring this out. Okay. We said the idea is run to completion and things, okay, and we put things in the event loop. Okay. So let's start off and look at all the function calls. Okay, at the very beginning of this program, this little, no, I don't want to copy you. Okay, at the very beginning, okay, we're in this kind of global context, so where you can think about it is we're running this function, all this code. Okay, so the first function we hit is console log. So we call this, okay, and this thing happens. Okay. The next thing we do is we call the function set timeout. Professor, doesn't this run? No, it does not run. Why not? Because what does it do? It goes and puts an event into the event queue. Okay. That event, when it gets executed, will call callback 1. However, we're not there yet. Why not? Because we run till completion. And so this is the function call. What does it do? It puts something in the event queue, but then we go on to the next call. The event queue does not get service because we're currently working on the thing that gets run to completion. So the next piece of code that gets run is console log. This is just a message over here. Oh, then what's the next thing that gets called? Set timeout function CB2. Does this get run yet? No, it gets put into the event queue. Okay, we're not going to go to the event queue because we're not done with this piece of code yet. Next line, console.log, this is the end. Okay, at this point, we've completed our processing. We've run to completion. No other code. Oh, there is more stuff to be run. There's stuff sitting in the event queue. How do you know that, Professor? Because we put it there. Function callback 1. Okay? After we're done with all this code, the JavaScript runtime will take this first event off the queue. Okay? And that's when it runs callback 1. Oh, cool. That's why that happens after all this thing. Now, why didn't callback 2 happen before callback 1? Because a queue is a waiting line. This thing got called and put into the event queue after this thing got put into the event queue. Oh. Well, that's interesting, Professor. Can we do interesting stuff with this? Yes, we sure can. And this is actually leads to a very nice generalizable way of dealing with asynchronous behavior. Okay, it's simpler than threads. Okay, but it can do good stuff for us. Okay, but like anything in asynchronous programming, it can be confusing. So let's take another look to see what we learned. So I'm going to try and create a clock. Okay. What I'm going to do is compare the clock I'm going to make based on the set timeout stuff with the clock that's running on my computer. Every time I go new date, okay, I get the current time from my computer. Is that right, Professor? Righty, righty. Let's try it. There's the web console. Okay. New date. It's Tuesday, blah, blah, blah. 4:53 daylight time. Let's try it again. Try it again. It's now 16:53:47. 12 seconds have passed. So we can get the clock time from our computer anytime we want by calling new date. So a lot of times I use this to time how long things take. Okay, so here, start time equals new date. Then in this little function thing here, I got elapsed time. New date, so that's going to be a time, minus start time, and it's keeping track of things in milliseconds. So I divide by 1,000. Okay, so I'm going to say my time. So I'm going to have a time thing. My time equals 0, starting at 0. Every time I run this function, it's going to advance time, okay, by 1 second. Okay, so here's what my plan. Okay, I'm going to call set timeout 1, 2, 3, 4 different times, each with 1,000 milliseconds. Each time it's going to call the advanced time, right? Okay, I'm going to make a clock this way. Okay, will I be successful? We will see in a second. Okay, so let's copy the code. Let's just double check what is all in the code. Oh, yeah, Let's just double check what was in the code. Sorry about that delay. Okay, remember the step at the top, just for timing purposes. We have this function that just advances, adds 1 to this global variable. Then we're going to double check how much time has elapsed and compare, okay, our start time, get the elapsed time based on the computer clock, and compare it with this time we're trying to do, because I'm trying to create a little clock, okay? This is not a good way to create a clock, okay? But I'm trying. Okay, so let's copy that. I said let's copy that. Okay, now let's run it. Okay, okay, so we're going to run the software. What? What? My time equals 1. Elapsed time equals 1.07. 007. My time equals 2. Wow, something's not working. This is really, really bad. I mean, what happened? What happened? What happened? Oh, wait a second. Set timeout. What does this do? Puts this thing into event queue. Okay. Puts this function to the event queue. Okay. And it says, wait a second before you do that. What's this call do? Puts this into the event queue. Okay. It says, wait a second. How much is the time between these two things? Microseconds, right? Because remember, it's run to completion. There's nothing that says this, we wait here until this completes. No. So what we did was we just set up 1, 2, 3, 4 things into the event queue, all set to happen in about 1 second from when we launched them. Hence, all these times are just trivial differences in 1 second of elapsed time, because that comes from the initial delay. Oh, so this doesn't count at all. No, it doesn't. These things all try and happen almost like in parallel. I mean, they're not. They happen one after another, but they sure, one doesn't get delayed a second, then another second, then another second. So this is a failure as a clock. Okay? Very bad. Okay? So, silly clock. Not a good clock by any measure. Okay? You can run this in Node and see it this way. You can run it straight in your browser. Okay, so what can we do? Well, we can nest the calls, right? We can go set timeout function. My time, see, we're going to have my time up here. Okay, so here's this function. Okay, this function, we're going to put a function in here. My time plus equals 1. Elapsed time, new date. Yeah, this looks familiar. Okay. And then, so this function is going to get called when? Oh, after 1 second. Then, oh, when we're done with this one, we're going to set another timeout. See, notice this one's nested within, right? Because we want this one to happen after this one. So this set timeout happens on the outside. Going to set this one on the inside. Okay. All these are nested. Oh, all these kind of repeat. I could kind of put a function, the same function kind of in here, so it wouldn't look quite so ugly, because this is all doing kind of the same stuff in here. Okay. But this at least lets us see what's going on. Let's see if this works. Let's nest those calls. Okay. That looks kind of complicated, Professor. Yeah, it is kind of complicated, isn't it? But we're nesting the calls. So functions calling function, nesting deeper. Okay. 2. 3, 4. It worked. I mean, yeah, this is not the way to get super accurate time, but look, we were able to make a counter that counted, and it kept as accurate to, hundredths of a second. That's not too bad. Can we do more? Can we do more? Let's see what it looks like if we want to do more. Okay, so it counts. It's not pretty looking code. Let's go for even more. Now, this is one of those word search type of things, or where's Waldo? Find the pyramid of doom in here. A pyramid of what, Professor? Let's see. Okay, so here I kind of tried to clean this up a little bit. I have this little function here, update time. I add to the global time variable. I subtract from the start time. So I pulled that out into a function. Okay, so the question is, what will this do? Set timeout, update time, set timeout. Oh, so it's nesting things, nesting things, nesting things, nesting things. Okay, look at all that nesting. Thousand, da, 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 da. Professor, yeah, I don't see a pyramid of doom in here. Well, let's try and see if this thing works. Then let's go back and look for the pyramid of doom. Okay, pyramids of doom. Okay. Pyramids of doom. Oh, you mean if I turn the computer on my head on the side, I see this structure here in the code of the indentation? Let's see if this works, though. 1, 2, 3, 4. Ooh, it's counting. Nice. Wow. But, gosh, is that ugly code. Okay, look at that. So, this structure of indenting, 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 getting deeper and deeper nesting is what is sometimes referred to as the pyramid of doom. Okay, so this is ugly, deeply nested code. Okay, we didn't deal with any we didn't even deal with any error conditions. Okay, now, Professor, this is kind of make-believe. Yeah, it is, but not completely. We're going to see cases where we really want to make sure things happen in certain orders when we go and do things across networks. Okay. When this gets deeper and more complicated, or in our extreme case that we did, this is sometimes called callback hell or the pyramid of doom. Okay. Now, there's nothing wrong with the mechanism underneath. What the problem is the programming syntax that we're using. Okay, so there's nothing wrong with the JavaScript event loop. Okay, it turns out that's going to be fine for us as far as the types of asynchronous program we're going to do. However, programming it with just callbacks, that gets to be pretty nasty quick. Hence, there is the new standard that we're going to have to use because of our interfaces in the browser and now in Node that we're going to use to make requests to websites actually use. We're not going to use a callback-based approach. We're going to use something called JavaScript promises. Okay, we'll get to those in the next lecture.